For a really long time, individuals have imagined what life might resemble in different universes. Considering the James Webb Space Telescope the most stunning telescope in existence, that question can finally be explored. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed a couple of remarkable anomalies from one of the planets in the system, Proxima B. These peculiarities, called artificial lights, have puzzled some of the best minds in science. But what are they? Do these lights suggest the presence of intelligent life? Join us as we examine the James Webb Space Telescope's startling discovery of city-like lights that could change everything. The only life we are currently aware of is on Earth. Since the beginning of civilization, humans have wondered if there is life elsewhere in the universe. To answer this interstellar question, American cosmologists Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. Its primary goal was to collect spaceborne radio transmissions. Radio waves can travel farther and are, therefore, more likely to be detected by the 42 radio telescopes that make up the remarkable Allen Telescope Array in the California mountains. However, for over 30 years, no significant extraterrestrial transmissions had been found. Following that, the James Webb Space Telescope's successful launch reinvigorated efforts to examine a range of invisible planets orbiting distant stars. As the largest telescope in existence, floating around 1 million miles from Earth and equipped with highly sensitive detectors, it has the potential to reveal groundbreaking discoveries. Decades ago, there were no known planets outside our solar system. Since then, more than 4,000 exoplanets have been discovered orbiting various stars. According to NASA, the universe could contain trillions of exoplanets. The earliest signs of something occurring far beyond our solar system might be found in extraterrestrial vegetation. The Galileo spacecraft, en route to Jupiter, turned its instruments back toward Earth and observed a clear indication of the presence of plants. It recognized the vegetation red edge, VRE, a biosignature, a mix of red and infrared light reflected by plants. For instance, a planet like Earth, covered in abundant vegetation, should exhibit a strong area of distinct marks that are easily detectable. The James Webb Space Telescope, JWST, will measure the VRE of distant Earth-like planets in the habitable zone around stars, which could provide critical signs of activity in an exoplanet's atmosphere. When light crosses a planet's-star boundary, the JWST may be able to detect it as it enters the planet's atmosphere. The missing frequencies would then be visible through spectroscopy as molecules and particles in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method could be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres similar to ours, characterized by a mix of oxygen, nitrogen, and carbon dioxide. By searching for elements that are not commonly found naturally, one might even detect intelligent life. For example, chlorofluorocarbons, CFCs, man-made compounds used in refrigeration and cleaning products, would likely be detectable by extraterrestrials studying Earth's atmosphere from a distant location. If the JWST finds CFCs in planetary atmospheres, it could indicate the presence of life. However, life on exoplanets likely won't resemble life on Earth. In some cases, even ordinary living organisms like extremophiles, species that can survive in extreme conditions where most other life forms would perish, might appear alien. This group of life forms, mostly microorganisms, can endure extreme environments, such as temperatures up to 250 degrees Fahrenheit or highly acidic conditions with pH levels below 3. Since planets are more likely to support life if they don't have extreme temperatures or acidic conditions, it would make sense to begin with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit stable stars. Our Sun is a yellow G-type star. These stars are rarer and usually have shorter lifespans. However, in our galaxy, the chances of finding planets orbiting red dwarf stars, which are more common, cooler, and dimmer than our Sun, are higher. Their long lifespans allow for the development of life and the evolution of complex organisms. About 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to Earth's Sun, which is sufficient to support the nearby orbits of its planets. The most promising opportunity to observe city lights outside our nearby planetary system lies with Proxima Centauri. A red dwarf star, 4.25 light-years from the Sun. Proxima is generally fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. In 2016, cosmologists discovered a planet with 1.3 Earth masses in the livable zone, a Goldilocks-like zone where the light force is ideal for liquid water. Proxima B orbits Proxima Centauri. However, the fact that Proxima B is tidally locked makes it a potentially airless, dead planet. It orbits its red dwarf star at a distance of just 4.6 million miles. This close orbit exposes it to intense solar winds, which can strip away its atmosphere. Nevertheless, Proxima B receives enough light to sustain temperatures and liquid water similar to those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, meaning it always shows the same side to the star, much like the Moon does relative to Earth. Proxima Centauri is about 18% the mass of the Sun and emits significantly less light. For a planet so close to its star, it receives only about 5% of the Sun's power. This situation might seem like a desolate wasteland, but liquid water could exist on Proxima B if the planet has an atmosphere to retain heat. Since the total energy it receives from the star is only 65% of what Earth gets, the planet isn't particularly ideal for life. It is likely tidally locked, meaning one side is perpetually warm while the other remains cold and dark, with extreme temperature variations. Additionally, the planet is bombarded with over 400 times the high-energy radiation that Earth experiences, including X-rays and ultraviolet light. This is due to its close proximity to Proxima Centauri. High-energy particles during stellar flares further complicate the potential for habitability. Unless Proxima B has a protective magnetic field like Earth's, the conditions may not support life. Despite these harsh conditions, Proxima B could still be a more livable world. Unfortunately, models suggest that the atmospheres of tidally locked planets may erode rapidly because volatile gases freeze out on the night side. On Earth, volcanic activity replenishes the atmosphere, and strong magnetic fields help prevent atmospheric escape. Since we know little about Proxima B's volcanic activity or magnetic field, we cannot predict whether the planet has an atmosphere. However, the presence of an atmosphere suggests the possibility of life. If Proxima B does have one, it could use solar panels on its day side to generate power to light and heat the night side, which would otherwise be too cold and dark for habitation. The discovery of Proxima B has sparked a race to determine whether it transits its star from Earth's perspective. Such transits would allow scientists to measure the planet's size and mass, which would help estimate its density and confirm its rocky composition. During a transit, starlight passing through the planet's atmosphere could reveal its nature. However, the chance of the orbit being perfectly aligned for observation is only 1.5%. The star's instability adds further complications. Cosmologist David Kipping of Columbia University notes that Proxima Centauri's intense radiation poses challenges for detecting Proxima B's potential atmosphere. Rocky planets absorb sunlight and re-emit it as infrared radiation. The James Webb Space Telescope, JWST, specifically designed to detect infrared light, could identify Proxima B's atmosphere. Additionally, the JWST's infrared capabilities, surpassing those of the Hubble Space Telescope, could even detect artificial lighting on Proxima B's night side, provided it is within a specific frequency band smaller than the star's light. Proxima B's day side might be heavily covered with solar panels, reflecting starlight. The extreme temperature contrasts between the day and night sides depend on whether the planet is bare rock or if its atmosphere and water circulate heat. Without an atmosphere, The day side would release all the energy it receives from Proxima Centauri as infrared light, while the night side would resemble a frozen wasteland. If the temperature differences between the two sides are less pronounced, it could indicate atmospheric circulation. Future space exploration and the search for life beyond Earth hold immense potential. The JWST may play a pivotal role in finding extraterrestrial life. As the telescope searches for exoplanets, it could shed light on the possibility of city lights far beyond the stars. While the JWST is a remarkable advancement, it is only the beginning of our deep space exploration journey. Challenges such as atmospheric conditions, stellar activity, and vast distances may limit clear or definitive signals from distant planets. However, the potential for discovery remains vast, especially as new technologies emerge and exploration methods improve. The study of Proxima B and other exoplanets continues to push the boundaries of our understanding. Every new discovery, whether it's a planet with signs of water, a potentially habitable atmosphere, or even traces of artificial light, brings us closer to answering the profound question of whether life exists beyond Earth. With the capabilities of the JWST, we may soon peer far beyond our solar system in search of signs of life, and possibly civilization among the distant stars. As the JWST continues its mission, we will gain insights into the atmospheres and compositions of planets like Proxima B. Its ability to detect faint infrared signatures could help us uncover not only the presence of water or an atmosphere, but also signs of life, whether microbial or intelligent.